Hi everyone, so this is a second video that was asked for me to do, which is problem 34 from chapter 34. It says, gives us this diagram down here and says, what is the net force, magnitude, and direction on each wire in figure 24.34? So here we go, here's wires 1, 2, and 3. I'm going to act like I'm looking at the wire from this direction, like this. And then I'm going to draw it like this. So it's going to be wire 1, wire 2, and wire 3. So here's wire 1. Here's wire 2 and wire 3. So wire 1, I can see the current is going into the page here. So it's 10 amps. And they're all 10 amps into the page. And each wire 1 and wire 3 are 2 centimeters away from wire 2. And then they're 4 centimeters away from each other. So let's see. Then the current goes into the page. So this is current. Should draw it maybe a different color. So let's do this. So here's current. Here's current 2. All the currents are the same, so I'll just say I. Whoop, wrong way. I can do this. So into the page, out of the page, and then into the page again. All right. I think I'm going to start with, so you want to find out the magnetic field. So I can use my right-hand rule, and I can see the magnetic field goes this way due to wire 1. Using the right-hand rule again, the magnetic field goes this way due to wire 2. And then again, the magnetic field goes this way due to wire 3. So I got basically clockwise, counterclockwise, clockwise happening here. Okay. And I think the first thing I want to address here, though, is the force on wire 2. So, well, first thing I want to find out is what's the magnetic field at wire 2. Well, wire 2 can't exert a magnetic field on itself, but it can feel magnetic fields from wire 1 and wire 3, and that could cause a force. So, okay. So, magnetic field due to... Let's start with 3, magnetic field due to 3. So here's the magnetic field due to 3. It would be pointing like that because the magnetic field go around and up like that around the wire. And then magnetic field due to 1 is going to do the same thing, but in the opposite direction because, again, the magnetic field goes like this. And so that's going to be magnetic field due to wire 1. And, right, the equation for that magnetic field is mu naught I over 2 pi r. And so I can see that these magnetic fields are going to cancel out. So these magnetic fields are going to cancel out because they're the same current, 10 amps, and they're the same distance, 2 centimeters away from each other. So they have the same magnetic field pointing in opposite directions. They're just going to cancel out. So what's the force on, and sorry, I should also mention to calculate the force, magnetic force is going to be, I think I'm going to use Bill. So, yeah, times the length of the wire. Oh, wait, are they? Yeah, magnetic force, that's what they want. So I got the length of the wire times the current times B, magnetic field. And I can see that these are just going to cancel each other out. So, yeah, so the magnetic force, so the magnetic field basically then here is going to be 0, and then 0 times anything is 0, so the total magnetic, so the force that it feels is going to be 0. All right, so I don't need to really worry about that then. So there we go. All right, and then I'm only going to find the magnetic force due to one of these, because basically then I can, oh, well, actually, no, I got to find the magnetic, so I'll find it due to, oh, yeah, sorry, my bad. Blah, blah, blah. So I'm going to find the magnetic force just due to one of these, because basically I can do the same thing over here, and I'll get a slightly different answer, and I'll explain what's going on here. So, okay, let's see. This distance here is 2 centimeters. And then this distance here is 2 centimeters. Oh, that's a consistent screw up right there. So there we go. And then I can let's see. So using my right-hand rule, I can find the magnetic field due to wire 2. So magnetic field due to wire 2 is going to point upward, like this. That's not right. It's going to point downward, like that. So this is the magnetic field due to wire 2. Right-hand rule again. Yep, that's right. And then magnetic field due to wire 3 on wire 1 is going to point upward. Notice I have it smaller, and I have it smaller because the currents are the same, but so the currents are the same, but the wire 3, keep screwing these things up. So this is magnetic field 3. The distance from wire 3 is twice as far, so it's going to make it smaller. All right. And so next up, I'm going to find the net magnetic field. That's just going to be B3 because it's pointing up minus B2 because it's pointing down. All right. Next up, to calculate the magnetic field due to a wire, it's mu naught I over 2R. So it's going to be R, I could call this R3. So this is R3, that distance. And then this distance here is going to be, this distance here is going to be R2. So this is R3 minus mu naught I over 2 R2. All right, make my calculation a little easier. I'll factor out my mu naught and 2. So this is going to be 1 over R3 minus 1 over R2. And then I'm going to plug all this into my Bill equation. So I could take all this, plug it into Bill, and I'll have the equation that the magnetic force is mu naught I over 2, and then I over R3 minus I over R2 times I times the length. And do they give me the length? They do. Sorry, I haven't mentioned. They give me a 50 centimeter length. All right. These i's will combine, so it's going to give me I squared, and then I think I can just plug stuff in and get an amount for this. So I squared divided by 2. Let's throw in the L over here as well, and so I got 1 over R3 minus 1 over R2. And this should give me my force. Okay, so I think I just need to plug in everything. So the current is 10 amps, so squared, 0.5 meters, 50 centimeters. Yep, 0.5 meters is the length, divided by 2. This is 1 over R3, which is 4 centimeters, so it's 0.04 meters. Minus 1 over R2, which is 0.02 meters. And then mu naught, I have to look up mu naught. I think it's 4, I'm going to say 4 pi times 10 to the negative 7. It's something like that. Let me look it up really quickly here. I always forget it. Yep, 4 pi times 10 to the negative 7. All right. 4 pi times 10 to the negative 7. And then I could plug all this in. So let's see what I get here. I'm going to get a value finally. 1 divided by 0.04. That minus 1 divided by 0.02 times... So 4 pi times 10 to the negative 7. Doesn't like pi. Sorry, this is taking much longer than I thought it was going to. 5, 7. times 100 times 0.5 divided by 2. I am getting a magnetic force of 7.86 times 10 to the negative 1, 2, 3, 4 to the negative 4. And that's newtons. And that's the magnitude of that. And hold on, I'm not 100% confident in my answer, so let me do that one more time. Yep, 7.86 times 10 to the negative 4, so that's checking out. All right, so that's the force, and there you go. Now, so the net magnetic field points downward, right? That's the net magnetic field points downward, right? And so now I can use my right-hand rule again to find out what the direction of the force is going to be. So I'm going to put my thumb, I'm going to use right-hand rule 2. My thumb's going to go in the direction of the current. So it's going into the page. My fingers point downward because that's where the net magnetic field points, and my palm is pointing to the right, or sorry, to the left. So my magnetic force points to the left. So it is going to feel a force, to the left. So it's going to feel a force to the left. So it's going to be repelled that way. And likewise, I am going to do the same thing over here, and the magnetic field on current 3 is going to be pointing, well, due to current 1, the magnetic field is going to be pointing downward. So this is the magnetic field due to current 1, and then due to current 2, it's going to be pointing upward. It's going to be pointing upward like that. So this is the magnetic field due to 2. So the net magnetic field this time is going to point this way. So here's the net magnetic field. But if you can see, the values are going to be exactly the same. The magnitude of the force is going to be the same as if I plugged it in here. Because nothing's really changed aside from the direction of the net magnetic field. But again, I can use my right-hand rule. I got my current goes into the page. The magnetic field points up. My fingers point up. And I see that the force points also, well, not also, but to the right instead. So there's the magnetic field, magnetic force on current 3. And here's the magnetic force on current 1. So current 2 feels no magnetic force. So I call this FB1. I can call this FB3. This is FB2 is 0. But FB3 feels a force of 7.86 times 10 to the negative 4 newtons to the right. And then for current 1 feels the same force, 7.86 times 10 to the negative 4 newtons to the left. All right. Hope that helped. Bye. Sorry. Continuing on here, I caught a mistake that I made here. So you're probably yelling at me from previously, but it's over 2 pi. I think I might have, I don't know what the heck I was thinking. I might have thought a loop, but anyway, it doesn't matter. Should have been a pi here that whole time. So this should have been not 2r, but 2 pi r3 and r2. So this is 2 pi, that gets factored out. 2 pi. What's nice is, if I would have done that, I wouldn't have had as big of a problem when I was calculating, because this pi would have just canceled out. Anyway, I need to take this value and divide it by pi. And when I do that, I get a magnetic force of 2.5 times 10 to the negative 4 newtons. And that should be the correct answer. So sorry about that. Hopefully you weren't yelling at me too much. Okay. But everything else stays the same. Everything else is exactly the same. I just forgot a pie. I'm sorry. All right. Bye-bye, everybody.